Okay, let's spend some time just practicing trig functions. And what I want to go through is how to graph transformations of trig functions. And it's really similar to what we just learned about transformations of regular functions. We're just applying them to trigonometric functions. And then we need to be able to come up with the equation of a trig function given a graph, and that'll help us to do word problems. Okay. So a couple of things here. First of all, this is what the graph of y equals sine x looks like. All right, the graph of y equals, we have to know the graph of both y equals sine x and cos x. But the graph of y equals sine x is a pretty good jumping off point. All right. Give me just a minute here. All right, so we're looking at the graph of y equals sine x, and it's shown over here. Now, some features of the graph of y equals sine x. So first of all, the period of a sinusoidal function is where if we pick one starting point, once it goes through one complete cycle, and one complete cycle for y equals sine x means starts at its middle value, what we call the axis of the curve. That mean value, or the axis of the curve, is the halfway point between the maximum point and the minimum point. So starting off at its mean value, going up to its maximum, back down to its mean value, down to its minimum, and back to its mean value again, that's one cycle. And the length of one cycle, how long it takes for one cycle to occur, is called the period. All right. Now, the period of y equals sine x is 360 degrees. More on that in a second. The amplitude of the graph is the distance from the mean value, same thing as the axis of the curve, the distance from the mean value to the maximum, or also from the mean value to the minimum. That's called the amplitude. For y equals sine x, the amplitude is 1. Meaning the maximum happens at positive 1, the minimum happens at negative 1. All right, so all of these things are key features. Okay, we have the axis of the curve, or the mean value, the period, and the amplitude. Now, I'm not going to really go through how to get all of this stuff in terribly large amount of detail. But you should know what the graph of y equals sine x looks like and the graph of y equals cos x. And so I'm just going to sketch both of those for you and highlight some very important points. All right, so first of all, we're going to scale off this grid as positive 1 here, negative 1 here, and then just roughly, this will be 90 degrees, 180 degrees, 270 degrees, and 360 degrees. All right, let's graph y equals sine x. So y equals sine x, how we remember this is y equals sine x starts at 0, 0. At 90 degrees, it stretches up to its maximum of positive 1. At 180 degrees, it's back down to 0. At 270 degrees, it goes to its minimum of negative 1. And at 360 degrees, back to its mean value. We have 1, 2, 3, 4, 5 key points that you need to know. And those 5 key points sketch out one complete cycle of the graph. All right, try your best not to make it a zigzag pattern. Make sure it's rounded at the maximum and the minimum. All right, when you draw it. There it is, 5 key points. That's the graph of y equals sine x. Now the graph of y equals cos x is the exact same thing, just sort of shifted 90 degrees. Let's have a look. The graph of y equals cos x looks like this. Rather than starting off at 0, 0, it starts off at the point 1, 0, and it starts off at its maximum value. The graph of y equals sine x starts off at its mean value right in the middle between the maximum and minimum. Whereas the graph of y equals cos x, that starts off at its maximum point. From there, at 90 degrees, it goes to its mean value. At 180 degrees, it gets down to its minimum of -1. At 270 degrees, back to its mean value. And at 360 degrees, we're back up to the maximum. So when we graph this now, this is what it's going to look like. All right, there it is. 5 key points, 1, 2, 3, 4, 5. Now for both of these, the graph of y equals cos x and the graph of y equals sin x. And first of all, it's important to see that one is a translation of the other, right? If we take y equals cos x and we shift it 90 degrees, if we shift it like 360 degrees, or if we take the graph of y equals sin x and shift it 90 degrees to the left, we'll have the graph of y equals cos x. So the two are translations of one another, okay? In either instance, this is for both of them, we know that the period for both of these graphs is 360 degrees. That's how long it takes for one complete cycle to happen. And the amplitude for both of these is equal to 1. The mean value, or the equation of the axis, in this case, is 0. And that's the halfway point between the maximum and the minimum. All right, so as a jumping off point, we have to know what both of these graphs look like. Y equals sin x and y equals cos x. Now, some other important things that we need to know before we start graphing these things. Every sinusoidal function, and when I say a sinusoidal function, I mean a wave function such as this one, it can be written in terms of sin x or it can be written in terms of cos x. And all those standard parameters of transformation apply, a, k, d, and c. And they act the same way that they do for regular non-trig functions. All right, so the meanings of parameters a, k, d, and c, we just reviewed that. A, vertical stretch compression by a factor of a. K is a horizontal stretch compression by a factor of 1 over k. Now D is a horizontal translation, a sideways shift. Now we're going to call that a phase shift when we start talking about trig functions. And C is a vertical translation, so that's an up and down shift. All right. Now, some other things about these parameters that are important. The A parameter, which is a horizontal stretch or compression, it also gives the amplitude of the graph. So whatever the value of A is what the measure of the amplitude is. The parameter K is really important because we can figure out what the period of the graph is depending on what that parameter K is. Now, there's a lot to take away there. You see, if I can show you with Desmos, let me just get Desmos up and show you just a quick sketch of what I mean here. Let's make sure we're in degrees, not radians. And I'll have to change my axis here. Let's go from 0 to 360. And our y-axis from -2 to 2. Just to set this up so it looks right. Okay, if I graph y equals sin x, this is what I have. Right, exactly what we might expect. But if we start playing around with the a parameter, so if I put an a value in front there, as I start to increase the value of a, we can see that all the zeros stay put. What changes is the amplitude. The maximum gets stretched up higher, the minimum gets stretched up lower. So when we make the a value something like 2, we can see that the maximum happens at +2, the minimum at -2. And as long as I don't do anything else with this graph, as long as I don't shift it up or down or sideways, we know that the maximum value happens at 2 and the minimum value at -2. So we have the amplitude value of 2. All right, if I make it something like -2, the whole graph is going to flip, and it's going to be reflected in the x-axis. All right, if I make it -1, we have a graph that's going to match y equals sine x, just reflected in the x-axis. All right, and then if I make the a value something like a half, right, we can see that it got compressed vertically by a factor of half. In either instance, no matter what a values I pick, right, if I make it y equals 1/2 sine x, or perhaps I'm going to do y equals 3 sine x, or maybe, I don't know, y equals 2.5 sine x. Doesn't matter, whichever one I pick. In either instance, the period of these graphs is always going to be the same. One complete cycle for all of these different graphs happens at 360 degrees. So the amplitude doesn't affect the period. Or sorry, the a parameter, the stretch or compression, doesn't affect the period. But if I start putting a k parameter in there, so y equals sine kx, remember the k parameter represents a horizontal stretch or compression. Right? So if I make my k value some number bigger than 1, my graph gets compressed horizontally. But when I compress the graph horizontally, the period changes. So right now, when it's y equals sine x, our period is 360 degrees. It takes 360 degrees for one complete cycle to occur. But when we start increasing that value of k, the frequency of the graph increases, right? So something like k equals 4, all of a sudden one complete cycle happens a lot sooner at 90 degrees. So the period shortens. And if we make our k value some number between 0 and 1, we can see that the period lengthens. So that has the effect of, if we expand the graph horizontally or stretch it horizontally, our period's going to increase. So because the k parameter affects the period, we use this really helpful formula to help us figure out what that period is if we have the k value, or figure out the k value if we have the period. So the formula is period is equal to 360 divided by k. The c parameter so the c parameter and the a parameter both could be calculated very easily using the maximum and minimum points. So if we have the maximum and we have the minimum, the amplitude is given by maximum minus minimum divided by 2. And then the c parameter is the same thing as the mean value. And we can figure out that c parameter by doing max plus min divided by 2. So coming up with the a parameter, the k parameter, the c parameter is very easy and formulaic. The phase shift is a little bit more challenging. All right. Now, the first thing that I want to do here is actually be able to graph a transformation of a sinusoidal function. So let's do that next. Okay, so here we have graph the function y equals 4 sine of 3 x plus 60 degrees minus 2. We want to graph that function. And once we graph it, we want to determine the amplitude, the period, the phase shift, and the vertical translation. There are lots of different ways that I could show you how to graph this transformed function. Lots of different ways. Some teachers teach one way, some teachers teach another way. Now, since we just learned about parameters of transformation and using mapping rules to help us take the original points of a parent function and change them to the transformed points, that's the method that I'm going to show you. Now, before we do that, what we need to remember, what we need to have is our base function. So our base function here is going to be y equals sine x. And if you remember, this is what y equals sine x looks like. And we're going to get the coordinates of those 5 key points. All right. So that's the graph of y equals sine x. And the graph of y equals sine x has, I'm going to make a little table of values. All right, x and y, these points are 0, 0. That's this point here. Then the next point is 90 degrees and 1, 180 degrees and 0, 270 degrees and -1, and 360 degrees and 0. Here are my 5 points. Now, next, what I'm going to do is I'm going to apply mapping rules according to these parameters of transformation. The parameters, of course, being A, K, D, and C. All right, before I do that, it might be best to graph the original sine function. All right, now I have a pretty expansive grid here that I'm going to use. So let me kind of scale out the grid a little bit. All right, so here's what I'm going to do. So this will be 2, 4, 6, 8, 10, and -2, -4, -6, -8, and -10. So my y-axis, I'm going by ones. Just make sure I have everything right. Okay. Now my x-axis, I'm going to scale them. I'm going to try to make as much use of this as I can. Looking at what I got here. I think the way that I'm going to scale this off is every box is 30 degrees. So 30, 60, 90. 30, 60, another 180. Then 270. Then 360. Okay, I'll keep going just to maybe show a few more cycles. So 360 plus another 90 would be 450. And then 450 plus another 90 would be 540. Okay, I'll do the same thing here. So -90, -180, -270, -360. And I'll keep going. -450, and then -540. Now, just for a point of comparison, I'm going to graph the function y equals sine x. Now, y equals sine x, according to this scale, is going to look kind of squished. It's going to look like this. So that's one cycle. Here's another half of a cycle. And then we'll continue this in the negative direction. Now, again, it looks really squished just because of the scale that I'm using. And I'm purposely doing this scale just because the transformed function is going to make use of these numbers. All right, so there's the graph of y equals sine x. All right, what we're going to do now is we're going to graph or transform the parent function. So here's my parent function, the table of values, the points that I just plotted. So that's y equals sine x. Now I'm going to create another table of values. And this one is going to be for the transformed function. And the transformed function, of course, has this equation. Y equals 4 sine of 3, x plus 60 degrees minus 2. So the parameters are all the same. They work the same way like we just investigated. The a parameter and the c parameter are going to affect our y coordinates. All right. So we're going to take each of these y coordinates and we're going to multiply them by by 4 and then subtract 2. So that's easy enough. 4 times 0 is 0, minus 2 is negative 2. 4 times 1 is 4. 4 minus 2 is 2. 4 times 0 is 0 minus 2. We have negative 2. 4 times negative 1 is negative 4. Negative 4 minus 2 is negative 6. And then 4 times 0 minus 2 is negative 2 again. So those are all my new y values. Now my x values are affected by the k parameter and the d parameter. K parameter and d parameter. So that would be 3, the k parameter, and the d parameter 60 degrees. So here's what we're going to do. We are going to take each of these original x values and multiply them not by 3, but by 1/3, 1 over 3. So every one of those x values gets multiplied by 1/3. And then we're going to subtract 60 degrees. Remember, we've got to take that opposite sign. So 1/3 times 0 minus 60 is negative 60. 1/3 times 90 is 30. And 30 minus 60 is going to be negative 30. Next, we're going to take 1/3 of 180. So 180 multiplied by 1/3 is 60. And 60 minus 60 is 0. 1/3 times 70 is 90. 90 minus 60 is 30. And then finally, 1/3 times 360 is 120. And 120 minus 60 gives us 60 degrees. So these are our new points. These 5 points, 1, 2, 3, 4, 5, got translated into these new 5 points. I'm going to plot these new points. So each of these blue points, so negative 60, negative 2. So remember, each box counts for 30 degrees, so negative 60 is over here, negative 2 is right there. Then the next point is negative 30 and 2. Negative 30 and positive 2 is right there. 0 and negative 2, that's this point. 30 and negative 6. So 30 degrees and negative 6 way down there. And then finally 60 and negative 2. So 60 degrees and negative 2. That's right here. So this is the graph. That's one cycle of the graph that I've just drawn right here. There's one cycle. And I have the 1, 2, 3, 4, 5 points visible. It shouldn't be a V shape like that, but it should be rather kind of rounded. So that's one cycle. If I wanted to draw more than one cycle, I could just kind of continue the pattern, right? So my next point would be up here. My next point would be here. Next one down there. Next one down here. And here's 2 cycles. And then I can keep going, right? 3 cycles would be right there. Okay, etc., etc., etc. What's important is that you show the 5 key points. You can show it in your graph, labeled properly, and also in a table of values. Now, looking at all this, we can see that from the equation, we should be able to determine most everything from our equation, all of the key features that it asks us. right? So this is what we have. Our A value is 4, so our amplitude is equal to 4. We have the K value is equal to 3. And so to find the period, that is 360 divided by 3, which is 120 degrees. So our period is 120 degrees. Our phase shift, so the phase shift pertains to the D parameter. So the D parameter is equal to negative 60 degrees. That's a phase shift. And we say that is 60 degrees to the left. And then finally, the C value is equal to negative 2. That tells us that the mean value is equal to negative 2. That's the same thing as the equation of the axis is y equals negative 2 is what I mean. Okay, so if you look at the halfway point between the maximum and the minimum, you can see that it happens at negative 2. So I just drew a purple axis there. I'm going to make it in dotted lines. So if the maximum value is positive 2 and the minimum is negative 2, the equation of the axis happens. Sorry, the maximum is positive 2, the minimum is negative 6. The axis happens right in between there, the halfway point of 2 and negative 6, which happens to be negative 2. All right, so that's how we graph these. All right, we graph them that way. Now, one important skill to have is the skill of being able to come up with the equation given the graph. So in this example, we were given the equation. We had to produce the graph. All right, we did that using mapping rules. The other thing that we have to be able to do is come up with the equation if we're given the graph. So I have two little examples that we can do to show you to do this. And for both of these graphs, what we're going to try to do is come up with both a sine equation and a cosine equation. All right, and really that's just varying the phase shift value. So remember, the equation of any sinusoidal curve is going to be y is equal to a sine of k x minus d plus c. The a parameter, the k parameter, and the c parameter are all very, very simple to do, or to find, I should say, because they're formulaic, all three of them. The a parameter is maximum minus minimum divided by 2. There's the formula we're going to use. So the maximum value, if we look here, it looks like it's, well, this is 6, 7, 8, 9, 950 looks like the maximum. Minus the minimum here, it looks like the minimum is about 250. So 950 minus 250 divided by 2. That's 350. So that's our amplitude. Now the C parameter, that's the mean value, and that also has a very similar formula. That's the halfway point between the maximum and minimum. So max plus min divided by 2. So this would be 950 plus 250 divided by 2. And our C parameter, 950 plus 250, 1200 divided by 2. Our C parameter is 600. And that kind of makes sense because if you look at the graph, you can see that that middle value is 600. And that's really the equation of the axis. Okay, so we have our A parameter, we have our C parameter. The next thing we need is our K parameter. Now the K parameter, we can find the K parameter using this formula. Period is equal to 360 over K. So if we know what the period is, we can figure out the K parameter. Now let's look at the graph. This graph starts here, and it completes one cycle right there. There's the end of one cycle. So it starts at 0 and it finishes at 4. After another 4 years, the graph completes another cycle. All right, so this graph is showing you the population level of some group of animals as it pertains to year. The period of this particular graph is 4. 4 years is the period. So we're going to substitute 4 in for period. We have 4 is equal to 360 over K. We're going to cross multiply. Okay, so 4 times K, that's 4K, equals 360 times 1, gives us 360. And we're going to divide both sides by 4. So K is equal to 360 divided by 4. We end up getting 90. So our K parameter is 90. So we have 3 out of the 4 parameters to work with. 3 out of the 4. To come up with the D parameter really depends on what type of a function we're using. If we're using a sine function, remember that a sine function looks like this. A sine function kind of starts at its mean value, increases to its maximum, decreases to its mean value, down to its minimum, back to its mean value again. This graph also starts at its mean value and increases to its maximum. So it looks like this already follows the pattern of a sine function, and so we don't need a phase shift if we're going to use a sine function to model this. So one particular equation that we could use for this graph is going to be y is equal to, I'm going to use t for time, y is equal to the a parameter, which we said was 350, then sine of, our k parameter is 90, so sine of 90x, no phase shift, and then plus 600. And there we have it. This equation that I've written here as a sine function models what we have. Now we could also use a cosine function to model this. Now the cosine function looks like this. So the cosine function starts at its maximum, decreases down to its mean value, decreases to its minimum, increases again, back up to its maximum, back up to its max. So that's what the cosine function looks like. It starts at its maximum and then decreases. Now this function doesn't do that. It doesn't start at its maximum and decreases. It starts at its minimum and increases. But can we find another point on this parabola? Sorry, not the parabola, my mistake. Can we find another point on this sinusoidal function? A maximum point such that when we pass that maximum point, the function decreases. So I see a particular point right there. Right? Here's a maximum point, and when we pass it, we are decreasing. And I see another one right here, a maximum point. When we pass it, we're decreasing. And yet another one here. All of those points represent suitable phase shifts that we could use. So let's go to the first one. This point over here starts or is a maximum point, and when we pass it, we are decreasing. Very similar to what the cosine function does. So this point would represent a phase shift of 1 year, would represent a phase shift of 1 unit to the right. So if that's the case, another possible function that we could use, a cosine function of course, would be y is equal to 350 cos of k value 90 Now we need that phase shift. So x minus 1, close bracket, plus 600. Both of these equations represent the exact same curve. Okay, one last example that we're going to do. I don't think I'm going to be able to get to the word problem modeling. So let's try this one. This graph represents the amount of daylight, hours of daylight, for a particular location as it varies by month. Okay, so we got to come up with the equation of this. So we need the a parameter. So that's max minus min divided by 2. We have got to come up with the c parameter and the k parameter. Let's find the max first. The maximum here is 16 minus the minimum is 8 divided by 2. So 16 minus 8 is 8. 8 divided by 2 is 4. Our a parameter is 4. The c parameter, that's the mean value. That's going to be max plus min divided by 2. So that's going to be 16 plus 8 over 2. That's going to be 12. So we have our a parameter, we have our c parameter. We're going to find our k parameter now using period is equal to 360 over k. Now let's look at our graph. What is the period? It looks to me like the period here, this graph starts at its minimum, increases to its maximum, and then comes back down again. There's one cycle, and one cycle occurs after 12 months. So the period here is 12. So we're going to write 12 is equal to 360 over k. And now we'll cross multiply. So we're going to get 12k is equal to 360. We'll divide both sides by 12. And so we have k is equal to 360 divided by 12. We end up getting 30. That's our k parameter. So we have a, we have c, we have k. The last thing we need is our phase shift. And the phase shift really depends on whether we want to use a sine function or whether we want to use a cosine function. Let's look at a sine function first. As I mentioned previously, sine functions start at their mean value. The graph of y equals sine x starts at its mean value, increases to its maximum, decreases to its mean value, down to its minimum, back up to its mean value again. So this is the graph of y equals sine x. Now this graph doesn't do that. It doesn't start at its mean value, but we can draw the mean value in, or the equation of the axis, just to get a reference point. We said it's at 12. So there's my mean value. And now on this graph, can we find a point on the curve that starts at its mean value and then increases to its maximum? So I see that point right here. That's a mean value point that then increases up to its maximum. So that point represents a phase shift of 3 months to the right, or 3 to the right. So one particular equation for this as a sine function would be y is equal to a value of 4 sine of 30 bracket x minus 1. That's that phase shift of 1 unit, or sorry, not 1 unit, but 3 units to the right. So let's erase that 1, turn it into a 3. And then plus the mean value of 12. So there's one particular equation that we could use. And another equation, if we wanted to graph it as a cosine function, once more, remember the graph of y equals cos x doesn't start at its mean value, starts at its maximum, and then decreases to its mean value, decreases to its minimum, back up to its mean value, back up to its maximum. So that's the graph of y equals cos x. So can we find a point on this graph that is a maximum that then decreases to a minimum? Well, I see that point right up here. So that's a maximum point, and as we pass it, we are decreasing. So if I wanted to model this with a cosine function, I would have to use a phase shift of 6 units to the right. So this would be y is equal to a parameter of 4, cosine of same k parameter of 30, but this time the phase shift would be 6 units to the right. So x minus 6. Close bracket, and then the mean value of positive 12. Okay, that's all I'm going to go through for trig functions. We have one additional thing to do here with trig functions, and that is to deal with a word problem that we need to model. Okay, I'll do that next week, but I'm going to leave you all with some work to hand in here with regards to what we just covered.